Okay, then welcome to the first of the two afternoon sessions of this workshop. The first speaker is Mathias Weller, who will speak about parameterized cops and robbers. Mathias, the floor is yours.
Hi, thank you very much for the invitation. I'm going to present a little bit of work that I did together with Niels and Caroline. And there will be also some results of other papers of Thomas and Jakob, and the most recent one of Niels and Petra. So we'll have, for the introduction, we have two important concepts. The first will be the cops and robber games that many of you might know from static graph theory, where basically we have it's a two-player game consisting of first a setup, as usual per games, where the cop player may place up to k cops on a graph. So, for example, like so. And then the robber player might place his token also on a node of the graph, but he only has one, so there's one robber. He might place him there. And after the setup phase, each player plays in turns, starting with the cop player, and each player may move their tokens by at most one edge. So they may also stay in place. And if at any point after the cop player moved, he manages to put one of his cops on top of the robber, then the cop player wins. Okay, so for example, the first turn in this particular example might look like this. Cop player might move his left cop there, his right cop there. And then since the robber has not been caught, the robber might still move, for example, there. And at that point, everything would start over. Like the turn, there would be a new turn, which would mean the cop player can move his or her two cops. At which point now the robber is going to be caught necessarily in the next step, because he cannot evade any longer. So that means that this particular graph, on this particular graph, the cops can win with two tokens. Okay, so that's cops and robbers. Why is that interesting? Because in static graph theory, this models a lot of important and successful parameters, such as tree and path width. And whenever we're talking about a decision problem of this game, because for now it's just a game, we say the decision problem is given a graph, can k cops secure a win on this particular graph? Which is shown to be NP hard in general on static graphs, but can be solved for each constant k in linear time. However, in the following, we'll just consider a particular case, namely the one where k equals 1. So the question is one cop enough to catch the robber? So the second part will be edge periodic temporal graphs, where we have one static graph, but all of the edges are labeled by sequences. And the sequences might have different length, as shown here. And when, like in time step t, the graph G at time step t contains an edge EI whenever the sequence assigned to this particular edge has a 1 at time step t, where this time step t is taken periodically over the sequence, which means that it just wraps around whenever it would leave the sequence, which is just modeled by this modulo here. We have a bit of a shorter notation, which just has this circle there, which just says, okay, take the sequence and prolong it indefinitely by repeating it, then take the index t of this prolonged sequence. Okay, so for example, time step 0, this graph looks like that. We only have, I have a mouse for, we only have this edge here, which does not occur because it has a 0 at position 0. Everyone else will occur. So, okay, in time step 1, everyone shifts 1 further. Now we have these two edges that have a 0 at their sequence, so they do not appear. And now when we go from 1 to 2, you will see that up here, the sequence wraps around. Okay, so while these other three guys, they just advance by one. Okay, so those are edge periodic temporal graphs, and it just continues like that. Well, here it's time step 3. Every one of the three guys of the length 3 guys will also wrap around, and so forth. And as you can see, at time step 6, at the latest, everything will be reset to the beginning because everything is periodic in the lowest common multiple of the length of the input sequences. Since our input sequences are 3, 2, and 1, the lowest common multiple will be 6. So at time 6, everything will be reset. Okay, I hope that's clear so far. So to combine these two, we're going to play cops and robbers on edge periodic graphs, which means that, well, it's just like the cops and robber games that I described earlier, just that the graph will advance as the game progresses. So in this case, before the game starts, the cop and the robber select their start positions. And again, we only consider one cop here. And then the game starts, which means that we're first going to play on the time step 0. And again, the cop moves first before the robber, so he moves on the one edge that is incident to his node. And the robber also moves to any of the two. Well, he wouldn't move down here, but he would move to any of those two. For example, he could move down there. So this concludes the first step 0, or time 0. And now we're looking at time 1, so the graph advances. And now again, the cop may move first, so he does, and the robber may not move because there's no edge incident to him at this moment, which means that he just waits and the graph advances. And at that point in time, the cop will be able to catch the robber. So we heard first about that game, and I think they actually invented it. Thomas probably knows better than me. On SoftSim 20, and in particular, Thomas and Jacob presented an algorithm that decides whether an input edge temporal graph is cop-win, so if one cop can catch the robber, in lowest common multiple of all the sequence lengths times n cubed time. But they left open the question whether that was NP, whether this decision problem was NP hard or not, which we took upon us to think about, and we thought, well, okay, that seems like a pretty hard problem. It is surely not easier than deciding whether the edge temporal graph is edgeless at some point. So we took the question of, so we actually, like, we reduced the cops and robber game, or the decision problem who wins, to the question whether the edge temporal graph is edgeless at some point. Or in other words, the problem, which we call periodic alignment, is given a set of sequences X, will they be collectively 0 at some point? And here I give you a yes. This is a yes instance here, and this is a no instance. Because here you see they are collectively 0, and those will never be collectively 0. Okay. In the review process, we got a comment from one saying that this is actually equal to something called tally intersection, where you have given a bunch of tally automata, and the question is whether they accept a common word. And what is a tally automata? It's basically something like a deterministic state, deterministic finite automaton, which accepts a language that can contain only one character, uni something, you know. And it has, basically its states are arranged in a circle, and a couple of the states will be accepting. So now you can imagine all the non-accepting states have a 1, and the accepting states have a 0, which is then exactly equivalent to our periodic alignment problem. Okay, so these guys are equivalent. and it has been shown that this tally intersection is NP-hard, which already answers the question together with this reduction, which I didn't show you, but maybe I'll have time. Answers the question whether the Kopsen-Rubber game is NP-hard, the decision variant. And we could also show, like, we showed a bit more of the complexity, parameterized complexity side. We showed that it's W1 hard for the number of sequences that have been given, and a couple of positive results where we showed that basically this is the greatest common divisor of all the input sequence lengths. So to the power of number of sequences squared can be solved by reducing to a multi-clustered clique. And it is also possible to solve this in a number of runs factorial by using an ICALP. Okay, so this relates back to Kopsen-Robbers with the reduction, showing that the decision version of Kopsen-Robbers is fairly hard, W1 hard for the size of the graph, even on quite restrictive instances, which means basically we managed to push the hardness into the sequences of the edges, such that the actual structure of the graph no longer matters. Right, all the hardness is in the sequences. Okay, so let's have a small look at how this all works with the periodic alignment, namely the relation of periodic alignment to clique and multicolored clique in particular. So multicolored clique is the problem, is the question of whether a given k-partite graph admits a k-clique. So one node from each partition. Okay, so this might be an instance of this problem, and we might be looking for this particular 3-clique there. So what we're going to do is first assign an order on all the nodes in each partition, and we'll make the partition pairwise prime by padding. And then we build our PCA instance by looking at each position individually, one by one, and setting a 0 if and only if there will be an edge between the corresponding nodes of the partitions. So if we look at position 0, we have the first two nodes of both partitions. There's an edge between them, so we put a 0, and we advance in the partitions simultaneously as well as in the string. Again, we have a 0, and now we wrap around. See, we just advance in the partition by 1, but in the A partition it wraps around. Okay, so there's again an edge. Now we wrap around in B again, and then finally there's no edge, so we set a 1. So this is the construction of our strings. We do this for all pairs of partitions. So here's the sequence for those two. Here's the sequence for those two. And then we can show with a bit of number theory that this particular PCA instance will have, like these sequences will have a 0 in common at some point, if and only if we can select one node from each of the partitions such that all the edges will be there. Okay, and this gives us that our periodic alignment problem is harder than multicolored clique, and it actually carries over the parameter. Like the k parameter is now the number of sequences. Well, not exactly. There's a square in there, but for parameterized reductions, it's still okay. And surprisingly, for us, or like in general, surprisingly, the thing works in the other way around as well. So we also have a reduction from PCA to clique. So imagine that this is our periodic alignment instance. Then we can construct a multicolored clique instance. Okay, so let's say we have this instance of periodic alignment, these 3 sequences. And again, the question was whether they will be eventually all 0 at some point. So what we can do is we have a partition for each of the sequences. And in each partition, there is
a node for each 0 in the particular in that sequence. So in this case, we have 2 nodes in each partition because each of the sequences has 2 zeros in them. And there will be an edge between 2 positions, I and j, whenever the position I in A and the position j in B will eventually overlap. What does that mean, eventually overlap? It means that there exists a position somewhere such that this position modulo the size of the first sequence is I, and this position modulo the size of the second sequence is j. And that is exactly the case if and only if I and j are congruent modulo the greatest common divisor between the size of, like, the length of the sequence A and the length of the sequence B. This is some kind of number theoretic magic with Chinese remainder theorem involved and so forth. But this works. So what we can observe is that we will have all the edges between these 2 partitions because their lengths are prime, which means that the GCD will be 1, which means that every 0 of the first sequence will eventually overlap with every 0 in the second sequence. However, for these 2 sequences, this is not the case because the GCD between 3 and 6 is 3. So the first 0 here leaves the remainder 1, I think, modulo 3. So yeah, so this one leaves 1 modulo 3. Which is the case only for the middle one here. So there's an edge only between this node and that node. And the second guy here leaves a remainder 2 modulo 3, but none of these other guys, none of these 2 zeros leave remainder 2 modulo 3. Okay, and the same thing can be done here. And then again, with the number theoretic magic, we can conclude that this particularly constructed instance of multicolored clique is a yes instance if and only if there exists a position where eventually everyone has a 0. Okay, so that proves that our periodic alignment problem is also easier than multicolored clique. So in total, this means that they're actually parameterized equivalent. And in particular, a thing to note is that for each 2 partitions, the edges between them decompose into GCD many bicliques, which means that we can solve, like we can just pick for all pairs of partitions one of the bicliques between them, and this will basically solve the clique instance. In particular, because there's this equivalence, this means that multicolored clique as a problem remains W1 hard, even if between each 2 partitions, the edges decompose into vertex destroying bicliques, which I found like super bizarre and interesting, but standalone result. Okay, so to drag this onto cops and robbers, this is a reduction from Petra and Niels. They did that. They basically described the cops and robber game on a cycle, where the bottom half here and the top half here, the edges there have sequences. Like we will construct over time the sequences of these edges, but for now, let's just say, okay, everyone has the first character of their particular sequence repeated k times. Okay, and these 2 edges serve as gates. They start out with 0 repeated k times. Then for administrational reason, he gets a 1, he gets a 0, everyone else gets 0. Okay, so maybe I wasn't clear about that. There's 1 copy of EI down here, and there's 1 copy of each AI down here. So they're actually like mirrored. Okay, so when we look at the game, cops and robber games, cop might put himself here because this is like a slightly more advantageous position. Now the cop tries to be as far as possible. The robber tries to be as far as possible. and so put some stuff there, and let's see what happens in the game that we have so far. First, everything here is 0, here is 1, and here is 0, so it looks like this at time 0. The cop may now just move along the edge. It's fine. No one else can do anything, so we get to time 1, where if all the sequences have a 0 at the first position, the cop is now able to pass all these guys and catch the robber. So that's why it's called phase 1 cop win if all the first positions are 1, sorry. However, so let's assume that's not the case. So he gets stuck somewhere, let's say here. What we now want is phase 2 to reset everything and go to the next position, basically. How do we do that? Well, for starters, we can just try and let the robber escape by allowing the gate to open. And then basically add K1s to all the edges down here and all the edges up here in order to let them go freely around their particular, around their hemisphere. So what might happen is the cop continues the cycle, which would incur the robber to also continue, which would now mean that the cop is at a disadvantageous position here because this one is like worse than that one. So he's better off going to his original position but mirrored, which means that the robber will go to his original position but mirrored. And then everything starts anew, basically. But with instead of the first position, it now has the second position. And so with this reduction, we basically can prove that on this on this graph, with this particular sequences here, which blow up by a factor of k, but well, that's okay. We get the hardness, like we get that the one cop can catch the robber if and only if at some point all the sequences will be 1, which is equivalent to saying at some point all the sequences will be 0. You just turn around the sequences. Okay, so that's the cops and robber games. We also have another reduction for this that has this particular layout, but I'm not going to go into details there. I'd much rather talk a little bit of conclusion, which is, so we learned that about this periodic alignment problem, which is actually, I find it as a funny problem, in particular because it's equivalent to this particularly funny version of multicolored clique. It's also equivalent to tally intersection, and it's W1 hard with respect to the number of the sequences, the number of sequences given. We also looked at this partial problem where instead of having all the sequences 0, you have to select L sequences, which have to be 0 at some point. So in that case, you can even show hardness if all the sequences have only 1 0. Notice that originally, like the periodic alignment problem here, this one is easy under this condition. Because remember the reduction to clique, in that case, you would have only 1 node per partition, and then multicolored clique becomes easy. Okay, however, our positive results, they also hold for this partial variant. In particular, FPT with respect to the number of, like the overall number of runs, because like with this condition here, we only have 2 runs per sequence, but the overall number of runs you get FPT. And we also have FPT with with respect to the pairwise GCD plus the number of sequences. This is also from the reduction to clique that I presented. Okay, so with respect to cops and robbers, this hardness induces a lot of hardness.
By the way, Matthias, would be great if you could conclude in, say, 30 seconds or so.
Yeah, that's possible. Cool. So there's a large amount of hardness incurred, which basically always says W1 hard with respect to the size of the graph. And remember this result by Thomas, the positive result. Okay, so open questions for the end. It's just, okay, all the usual, find a good parameterization. Is there anything about kernelization? Because we don't know anything about kernelization for periodic alignment. Can you like compress the sequences maybe? Or cut it, like kick out some sequences? We don't know. Also, the question is open whether it's in NP. It now has been shown that it is actually in P space, but like the periodic hops and orbits, but we don't know about containment in NP. This one is pretty easy for the containment in NP. And of course, the usual problems for variance where you have different types of rubber sculpts and so forth. And that's it from me. Thank you very much.